Hello, Pre-Calc. Here we are watching this after Monday's class, the 27th, and we're solving log equations. To do that, there's one key you have to recall from one of our previous videos, and that is, what is this equal to? Suppose we have 10 raised to the log of base 10 of 100. And I showed you that special logarithm earlier. Do you recall what it was? Well, you can look at the logarithm in the exponent and you see that 10 raised to what is 100? 2. So this whole thing is a 2. 10 raised to the 2 is 100. So you can see the relationship there so that you can apply it to 1 when you don't know the logarithm in the exponent, such as e raised to the ln of 3. So when you have that, that means this is base e, it's understood. So the exponent is the number I raise e to get 3. So what if I raise e to the exponent that I raise e to get 3? I'll get 3. It's as if this undoes this and you end up with 3. That's not a real good rendition of what's happening, but it might help your memory. So keep that in mind. We'll do one more. We'll say 5 raised to the log of base 5 of 21. So what is that? It's as if this undoes this, and we get 21. So we're raising 5 to some exponent to get 21. It's not 1, because 5 to the 1 is 5, too small. 5 to the 2 is 25, too big. So it's somewhere between 1 and 2, closer to 2. I'm not sure what the exponent is, but if I raise 5 to that exponent, I will get 21. Alright, it's a hard concept to teach, but it is key. So that's the key to tonight's lesson. Alright, keep that in view, and we'll solve our first log equation together. We'll say log x equals 3. The command is solve for the unknown. We'll keep x as our unknown, and some of us get upset when the exponent is not x. So don't want to upset anyone. So this is the unwritten base of e. So I'm going to exponentiate each side. I'm going to make this into an exponent and this on an exponent of that base. So I'm going to take e and raise it to the ln base e of x equals 3 to, e to the 3. Do you see? These two quantities became exponents. That's why I exponentiated both sides. It is mathematically sound as long as you pick the same base, and these become exponents to the same numbers. Then it is true. However, it's wise to pick the base that you're using as the number that you're raising these exponents from. So let's say that again. When you pick a number, these are going to become the exponents to a number. When you pick those numbers, it should be the base of the logarithm that you're working with. Because now we can use the key. The key is, what's e to the ln of base e of x? It's as if these cancel. X equals e to the 3. E is a number a little less than 3. So when you cube it, if you put e into the e cubed into your calculator, you will get the correct, you'll get an approximation. But I like this because it is exact. So 2.7 raised to the 3 or e raised to the 3 will give you an approximation. Alright, let's try another log equation. And this will be ln square root of x plus 1 equals 1. X plus 2 equals 1. I'm going to exponentiate each side, and those exponents are going to be on the letter e again, because I'm using a base e logarithm. E raised to this equals e raised to this. These became exponents on the e. So now this, what is e raised to the ln of e of x square root of x plus 2? It's x plus 2 equals e. We're almost there. We just have to peel a few more onion layers off to get down to the x. Square both sides. You get x plus 2 equals e squared. And move the 2 over by subtraction. That's what x equals. If you put it in the calculator, you square e and subtract 2, you get something around 5.39. But that's an approximation. This is exact. All right. 5 log x minus 2. This time the log is not ln, so I'll show you what to do with that. X minus 2 equals 11. All right. To solve that, before we can exponentiate both sides, that will get rid of the log, we have to have log by itself. So this expression has to be by its lonesome. So I'm going to divide both sides by 5. And now I can exponentiate both sides. I do that to get rid of the log. So I note that this is log to the base 10. LOG is understood. So I'm going to exponentiate on to the number 10. Do you see how these two quantities became exponents to the number 10? That is mathematically okay. As long as the exponent, they become exponents to the same number, it's mathematically sound. I picked the number because we were using a base 10 logarithm. Alright, so what is 10 raised to the log of the base 10 of x minus 2? Following your key principle, it's x minus 2 equals 10 to the 11/5, and add 2 to both sides. So you can take that on your calculator. 10 to the 11/5 plus 2, it comes out to a little more than 160, but this is exact. So I'm very happy with that. Alright, next one. Log to the base, log LOG again, so log x plus 4 minus log x equals log x plus 2. Alright, before we can go any further, we can't exponentiate both sides until there's 1 log or less on one side and 1 log or less on the other side. So I have 2 logs here and 1 log here. So I can combine these two by log rules because logs rule. When we subtract 2 logarithms, we can write them as 1 logarithm with the arguments divided. And that's one of our 3 log rules, so we pull that out. And over here, it remains the same. Alright, now I have base 10 logarithms going, so I'm going to exponentiate both sides. So I'm going to have 10 raised to the x plus 4 over x equals 10 raised to, I'm sorry, the log, I forgot the word log. This whole thing becomes an exponent. 10 raised to the log x plus 2. So you see this became an exponent of 10 and this became an exponent of 10. So this is a base 10 logarithm. So one undoes the other. We get x plus 4 over x equals x plus 2. You may be able to see how to quickly go from here to here, but I won't mention it. I want you to know why, because we really have exponentiated both sides, used this key, and we end up with this. So now we have to just solve that for x. I want to get rid of the divided by x portion. So if I multiply through by x, I get x plus 4 equals, what's x times x plus 2? X squared plus 2x. I'm going to move the x over and the 4 over, set it equal to 0. And then I have to solve that. Unfortunately, it's not solvable by factoring. So we pull out our quadratic formula, which is never far away from our minds. X equals minus b plus or minus square root b squared minus 4ac all over 2a. Alright, so somewhere in your math past you know the quadratic formula. Your a is 1, the coefficient, b is 1, and c is minus 4. That comes out to be negative 1 plus or minus square root of 17 over 2. And that is the correct answer, except there is something that happens with this logarithmic equation that hasn't happened with any of the others so far. And that is the negative 1 plus square root of 17 over 2 will give us a positive number somewhere, I think, around 1.6. And I'm not sure what negative 1 minus the square root of 17 over 2 is, but I'm positive that it's negative. So I'm going to get a negative number. And when I put a negative number back into the original equation, way back up here, this value right here, you're going to put in that negative number here, here, and here. I'm not sure about here and here, but I am sure right here that log of a negative number no can do. Because the log graph, remember how many you used to graph? The log graph would start here and come through this number and go like that. Notice all the x values for the logarithmic graph are positive. We cannot take the log of a negative number. So if your answer creates a negative argument after the word log, we must not count it. So whatever that negative number is, we have to discount it. What about 1.6? When I put it in here, I get a 1.6 plus 4. That's positive. That's fine. Here, a 1.6 plus 2. That's fine. Here, a 1.6. As long as your arguments are positive, we can accept them. If they create a negative one, we cannot. Therefore, I'm going to ask you to look back on the ones that we've already written down in our comp book and see if they create negative arguments. Alright, if you look back, you'll see that the 160 about for that one, and the 5 for the 1, and I forget what the other one was. When you put those back into the original equations, they do not create any problems at all. But we have to check every single time. Alright, I didn't show you that on the first couple ones, because I didn't think you were ready to bear it, but now it came up, so we definitely have to bear it. Alright, let's do it one more for good time's sake. Two log to the base 5 of 3x equals 4. And the command is solve, so we want to know what x equals. So we will recall that before we can exponentiate both sides, the log expression has to be by itself. So I'm going to divide both sides by 2. Log to the base 5 of 3x equals 2. And now I'm going to exponentiate both sides. And I'm going to use the base 5 for my base number. This became the exponent of 5, and this became the exponent of 5. The reason why I need a 5 here is so I can use this key. 5 raised to the log base 5 of 3x is just 3x equals 25. So I divide both sides by 3 and we get 25 thirds. We must check that. So I'm going to go back, at least mentally, and ask myself, here's the argument. Argument is that to which the word log is applied. It's applied to 3x. If I substituted a 25 over 3 in there, I will not get a negative argument. They're both positive numbers. So therefore, check. So when you do this work, you must check and see if your argument is positive. Put a check mark beside it to show me that you did check it, at least mentally. Alright, that's it. You will see that solving logs is as easy as falling off a log. So, we'll be falling off our logs on Tuesday. So, till then, over and out.